Have you ever just stopped and wondered how your computer does it all? Seriously, you've probably got, what, a dozen browser tabs open right now? Maybe some music playing, a document you're working on, and all those little background things just humming away. It feels like pure magic, right? Well, it's not. It's actually a beautifully choreographed dance, and today we are going to peek behind the curtain and see exactly how the magic happens.
Yeah, this is the big question. How does one machine with a finite amount of brain power create this perfect illusion of doing everything all at once? The secret, it turns out, is in the hidden life of something called a process.
So here's how we're going to break it down. First, we'll look at the computer's juggling act. Then, we'll explore a few different models for how it all works, starting super simple and then getting more complex. We'll even meet the traffic cops that direct everything. And finally, we'll see why this whole invisible dance is the bedrock of your entire digital life.
Okay, first things first. When you double-click an icon, you're not just running a program. You're turning a passive set of instructions into an active process. Think of it like this. A program is like a recipe in a cookbook. It's just sitting there. But a process, that's you, in the kitchen, actually cooking. You're grabbing ingredients, firing up the stove, following the steps. It's this active thing that the operating system has to manage. Now, to understand how the OS manages all this cooking, computer scientists use a few different models. We're going to look at 3 of them, building up our understanding as we go. We'll start with the most basic one, a simple 2-state model.
Then we'll level up to a much more realistic 5-state model, which is kind of the industry standard for most modern systems.
And then just for fun, we'll peek at an advanced 7-state model used for really high-performance stuff. All right, let's start with the basics.
All right, let's dive in with the simplest way to look at a process's life, the 2-state model. You can basically think of it as a light switch. It's either on or it's off.
So in this model, a process is either running, meaning it's actively using the computer's brain, the CPU, or it's not running. That's it. It's either doing work or it's not. Super simple, right? But this simplicity actually hides a really important problem.
I mean, think about it. What does not running really mean? Is a process that's paused because it's waiting for you to click a button the same as a process that's all fired up and just waiting for its turn? No way! Lumping them all together under one label is just, well, it's not very efficient. We need more detail.
And that is exactly where the 5-state model comes in. To manage everything way more effectively, operating systems broke apart that vague, not running state into a few very specific, very useful categories. This gives us a much clearer, more realistic picture of what a process is doing at any given moment.
This life cycle has 5 distinct stages, and it covers a process from the moment it's created to the moment it's gone. Let's walk through what each of these really means.
First up, we have new. This is literally the moment a process is born. The operating system creates a kind of ID card for it, called a process control block, or PCB. This thing holds all its vital info. But at this point, it hasn't actually been moved into the computer's main workspace, the memory, just yet. It's just an idea.
Next is ready, and this one is so important. A process in the ready state is fully loaded into memory. It has everything it needs to go. It's just sitting in line waiting for its turn on the CPU. Think of it like a sprinter, down in the starting blocks, muscles coiled, just waiting for the starting pistol.
And bang, there's the pistol. Running is the state we all picture. The process has been picked, and its instructions are actively being crunched by the CPU. It is off the blocks and flying down the track.
But sometimes a process needs to take a breather. This is the waiting or blocked state. It physically can't continue because it's waiting for something else to happen. Maybe for a file to finish downloading, or for you to hit a key, or for some data to come back from the hard drive. It's basically pulled over for a quick pit stop. And finally, we have terminated. The process has crossed the finish line. It's either done its job or you've closed it. The operating system then does a cleanup, freeing up all the memory and resources it was using for the next process in line. The race is over.
So we have these 5 states. But how does a process actually move between them? It's not random. It's all managed by some really important parts of the operating system that act like traffic cops, and they're called schedulers.
This flow is what makes modern multitasking even possible. So a process gets admitted from new to ready, then a scheduler dispatches it to running. If it needs something, it moves to waiting. Now pay attention to this next part. Once whatever it was waiting for happens, it goes back to ready, not straight back to running. It has to get back in line and wait its turn again.
This constant, high-speed movement is the very heart of the system.
Now, it's not just one traffic cop. There are actually 3, each with a very specific job. The long-term scheduler is kind of like the bouncer at a club deciding how many processes get let into the ready line at all. The short-term scheduler is like the DJ, picking the very next process to hit the dance floor, the CPU, and it does this hundreds, maybe thousands of times a second. Then you have the medium-term scheduler, which can actually kick a process out of memory for a bit to make room for others. Okay, now that we've got the 5-state model down, let's just briefly level up. That medium-term scheduler we just mentioned, the one that can swap processes out of memory, well, its existence actually creates the need for a couple more states for even finer control, which brings us to a 7-state model.
This advanced model adds states like suspend ready. Now, this is a process that was totally ready to run, but to free up precious RAM, the medium-term scheduler temporarily booted it to the hard drive. It's still ready to go, but it has to be brought all the way back into memory first. This is a super important trick for stopping your computer from grinding to a halt when you have tons of apps open. It's a trade-off, sure. It's slower to bring it back, but it keeps the whole system from crashing.
All right, we've talked about states, transitions, schedulers, a lot of technical stuff. But let's pull it all back together and answer the big question. Why does any of this matter? Well, because this completely invisible choreography is the absolute foundation of your entire computing experience.
You know, this quote really just nails it. This whole system of states isn't just theory. It's the practical, real-world engine that makes your computer feel fast and responsive. It makes sure the CPU is always busy, that no single app can hog all the resources, and that your experience feels totally seamless.
So, the next time you're effortlessly jumping between a game, a video, and your browser, just take a half second to appreciate the lightning-fast dance happening under the hood. That constant flicker between ready, running, and waiting, all orchestrated perfectly to create that feeling of instant, seamless magic. Makes you wonder, what other invisible systems are making our digital lives possible? That's a thought to take with you.